Looks like we're just about there, folks. I think I forgot to ask while we were waiting. Does anyone have any questions at the moment? Okay, we'll run the clock and get started. Well, it looks like we can start. Welcome back, everyone. This is day 2 of the class, so we've got something like only about 50 more class meetings and we'll be through all of it. So we're getting down day by day. For today's class, we're just going to continue on our section 7.1. In case we run through all those problems quickly, I try to always have in the next section just ready to go right down below. So think of these as sometimes usually just posted early, kind of as a just in case. Also down below, I post always the homework assignments together with it. So if you wanted to get started working ahead, this is what the section 7.2 assignment set will look like. Let's see. Other things to mention is we really didn't do too much last time when we came in on Monday, but we did talk a lot about the differential. So sometimes before class starts, I just doodle a couple things that we're about to work on or that we just worked on. And the differential is a pretty interesting equation. We take an original expression, y is f of x, come up with this equation. It's literally a differential equation, but it has on the left a distinct symbol dy, on the right another distinct symbol dx, and that's really very confusing. They are symbols just like ordinary x in algebra. The confusion is down here. Dy and dx are highly context sensitive. That's a hard word. If you write out like this, and you're meaning the derivative, the limit as h goes to 0 of this difference coefficient, dy dx cannot be separated. It's all one symbol, all on its own. So these are weird expressions. It takes a minute just to get your mind used to them. So another thing that's tricky in calculus is not just the notation, but how the notation changes by context as well, all at the same time. But the reason we're talking about differentials so much is in integration by parts, we take two differentials. Well, we deal with two differentials. For one, we calculate a differential, and for the other, we solve the differential. In other words, solving a differential equation in a pretty interesting sense. But that's my announcements to start us out today. Any questions or comments at the moment? Okay, so chapter 7 is kind of tough at start. We're really just picking up integration techniques. We're not going to try to run through it too quickly, since some of these sections are a little bit tougher than others. I would say surprisingly 7.2 is a pretty tough section, mainly because all we're doing here is reviewing trigonometry as we deal with integrating trigonometric functions. So if you look at the trigonometric identities here before class, do a little bit of review on trigonometry if you feel rusty, it's a big help in 7.2. But here's where we left off. We solved the antiderivative of the derivative of x times sine x prime. We rewrote that in Leibniz notation just to get a better view of it. And the trick was, if you integrate the derivative, you just get the integrand back. We have to add the arbitrary constant to get the full family of all antiderivatives from that indefinite integral. We'll practice out a couple more and then begin our integration by parts technique. After we get to this is where really Calculus 2 starts in earnest. We'll do several problems just doing indefinite integrals, and then a couple more with the definite integrals just to see how the process goes in this kind of situation. So let's begin all the way up here. This problem on the left, it turns out to be a U substitution, kind of like the first problem we solved on these notes. But I mentioned before, there are occasions where the author takes something like this, which is a U substitution problem, and does it essentially in one step. I want to describe how that goes because that's taken as a shortcut often enough in the book. It's helpful to be familiar with it. That's helpful for us as well in our own work, so we're not bogged down on a U substitution every time this one comes up. But let's practice the U substitution just for the sake of the review, and then we'll show the shortcut method. So if you're integrating, sine 3x dx. This is a pretty fast u substitution because the thing inside the function is linear. We will probably want to try u equals 3x. Take the differential of that u. We now have du is 3 dx. Well, the 3 there appears as a 3x, but we don't have 3 as a coefficient in front. So oftentimes our author would go back to this differential equation, divide out the 3 to get a third du equals dx. So that dx right here by the red dot is just going to turn into a third du. And now the whole thing is sine u times a third du. Now this is a pretty fast integration at this point. The antiderivative of a sine function is a negative cosine function. So we have negative 1/3 cosine u plus a constant. And the key thing that we mentioned last class is u substitution can't end at this step. We have to go back, undo the substitution by writing this as negative 1/3 cosine 3x plus the constant. So that's our second u substitution of the entire semester. But there is a huge shortcut here that we ought to describe right away. Any questions at all first with the sketch on work on the right? Okay, so here's where the shortcut comes into play. The major thing to notice is the 3x, this whole thing is a linear function. When a linear function comes up as the inner function and you're trying to integrate, this is the great time to just say the output should involve the antiderivative of sine. That's going to be a negative, give it a little bit of space, cosine 3x. But because of that 3, if we check out this problem by differentiating it, the chain rule comes into effect. We differentiate this whole thing, derivative of a negative cosine will become a positive sine of 3x, but then we multiply by the derivative of a 3x, which is now 3. There's no 3 in front, and so the thought here is place a 1/3 there, and now you're in business. That's all this integral problem really turned into. Same idea over here. If there's a 3 in this location, you should expect a 1/3 to come out in your total answer. Well, any questions with that so far, folks? Okay, although it's an encouraged shortcut, you don't have to take it, but I encourage you to think about it. Whenever the author uses this kind of method, it's usually a great approach. I often don't do that approach if it's something like this, x squared more than linear. Sometimes the author does do shortcuts there, but I'll always show the full process just for the sake of filling out the notes, really. Well, we did it, folks. Another thing you could do with this problem if you really wanted to, I would say if this is an exam situation, only do this if you fully solved your exam, you do have extra time. Here is the check. The check is now, well, if we found an antiderivative through this expression, then we just check by differentiating whatever we put out. So let's take d by dx, negative 1/3, that 3 looks kind of weird, let's put it that way, cosine 3x plus a constant. Calculus 2 is kind of interesting in the sense that we focus so much on integration at the start of the course, it's easy to get a little bit rusty on differentiation. So sometimes doing these checks is just good to keep up on differentiation itself. So if we differentiate, first property is the constant multiple rule. That negative 1/3 just stays right put. If there was a plus in between, though, it would vanish and go to 0. That would be the derivative of a constant rule. So negative 1/3 stays put. Derivative of a cosine function becomes a negative sine function. But the input here is more complicated than normal, so we have to multiply by the derivative of that input. The input's 3x, it copies down directly here through the chain rule. It goes down here where we differentiate. But if all you put down on paper is 3 because you anticipated that differentiation, I'd say good on you. That's the right step to take. This is showing the step in the middle. So So far, we have double negation. This is turning into a positive quantity. 1/3 is going to cancel with a 3 after we differentiate. So this all turns into, well, let's actually take the step. 1/3 sine 3x times 3. And at this point, I would just stop right here. Our goal is to show that the integrand is what we get when we differentiate. By this point, I'm convinced this is the end of the check, and we're pretty happy. Well, we did, folks. That's our first integral to start us out today. Any questions at all about this one? Okay. In fact, this shortcut is such an important concept. Let's throw in a bonus problem right in the middle. Let's say that this is part C, part 2. Let's do another one, antiderivative, and let's make it, say, e to the power of 17x. So if you were to find the antiderivative of this thing, you need the antiderivative of e to start out. So we would go like this. 17x would go in front. But if you differentiate this thing through the chain rule, you would get e17x first. You'd multiply by the derivative of 17x, which would produce a 17 right in front. We don't have that here, so we take the same kind of shortcut. To make this totally correct, throw in a 1/17, add a constant, and just like this and this canceled through the chain rule once we did our check, the 1/17 and this will cancel once we do the full chain rule on this problem. So that's just another look at that type of shortcut. Well, we could do these all day, but we've got other problems to take a look at. So let's get on to the next one. Part D is a massive trick question, in my opinion. It's mostly just for fun, but it's a good reminder of what is the difference between the indefinite integral. This is missing limits of integration. So the output is a function, well, a whole family of functions indexed by the constant c, any real number. This one's different. This is a definite integral. We have limits of integration from a lower limit of 0 to upper limit of pi. So the result of this would just be a real number. So any volunteers for what this whole total expression should come out as? It would be for, well, we would not necessarily want to solve this, but we would have to imagine what is it, and then what's the answer after you differentiate it? Well, not quite, because the output of this one right here would be just some real number. So we're taking the derivative of a constant, and it's kind of an unfair problem in a certain sense because integration by parts is to help us actually solve that antiderivative. So we need one more concept to really make this go through. Let's maybe put a review problem on the right to help us with the trickier problem on the left. If we had a function that goes y equals, say, 5, then we could say immediately dy dx, or you could just say y prime if you prefer, has to be 0, because this is a constant. The derivative is the slope of the tangent line, but a constant function like that is horizontal. Its slope is 0 everywhere. Let's do output of 0 on that derivative. This could look even worse, like say y equals cosine pi. These get really confusing, but cosine pi is just a real number as well. It's -1. So y prime, or dy dx if you prefer, still 0. The idea is, if this thing is a constant, the derivative is automatically 0, and that is true. This is a constant. We can solve this one if you're curious on what it would evaluate to. So because it's constant, derivative is 0, just like how we're getting 0 here on the right. Really kind of a strange problem in a certain sense, but does that make sense on the idea we used here? Okay, I'm not in the habit of asking random trick questions like this one on actual exams. Again, think of this as a review problem whose major purpose is telling the difference between this. The answer is a function, which you could differentiate. But this one, the output, where the curly braces are, is just a number. Its derivative is automatically 0. And compare that against, say, this one right here. Well, it was indefinite. We were just taking the antiderivative of a derivative. That's why we didn't get 0 as well on this one as well. But those are the major kind of things I want to talk about before we got into integration by parts. The biggest takeaway is U substitution. It does get used quite a lot in this course, and being familiar with differentials is extremely important as well. Well, let's go down to the exciting part of section 7.1, integration by parts. So much like U substitution, it has a purpose. It's trying to unwind the chain rule process. Integration by parts is trying to unwind the product rule process. We don't have an analogy for the quotient rule process. We would take a quotient and rewrite it as a product if we had to, and run it through the integration by parts process once again. And this is the whole spiel. Integration by parts is that. That's pretty tricky to get a handle on. And so my thought on this was, let's do our derivation on this just to see how this ought to go. We do not do a lot of derivations in this course. I think we do a total about 4 or 5, depending on time, sometimes a couple less. The only times we really do a derivation is if there's some interesting concepts to connect, if the derivation is rapid, and there's something we can get out of it. This is one of those situations. If you're doing integration by parts, we start off here. It means you're integrating two differential functions multiplied together. But notice the format. U equals f of x, v equals g of x. We'll start with that. We have a table. U is f of x. On your table, I know this looks pretty weird, go down a line and right and go v equals g of x. There's a purpose to this table. This is the type of table we write out when we go to do integration by parts using this technique. So on the left, we calculate a differential. Du is f prime of x dx. Again, this is the real table that we use when we integrate by parts. On the right, this is a value v equals g of x. We can calculate its differential and go dv equals g prime of x dx. So this is our start and integration by parts. Pretty much our step 1 in a certain sense, but we'll write those out when we do a full problem. Next thing we do is, well, we said integration by parts has a purpose of undoing a product rule. So if we're going to derive it, we just need to write down the product rule. Let's go like this. We're taking f of x times g of x, excuse me, put a prime here, but put a whole bunch of white space in front, kind of like that. The result to this is going to be f prime of x, a little bit of white space before your f prime, times g of x, then put a little bit of extra white space before the plus. We're going to fill in some extra symbols here. And then it's f of x, g prime of x. So here we have the ordinary product rule. Here's the fun part. We can just take this whole thing, integrate both sides of the equation. So what we do to one side, we can do to the other. We're not violating anything algebraically. So integrate the left will look like that. It looks really complicated, but this is one of our first exercises on these notes. It's the antiderivative of a derivative. All we get back is just the integrand when we do this part. So now next, on the right-hand side, integrate this with respect to x, so dx goes in. Integrate this with respect to x, so dx goes in as well. So this is our first step in integration by parts. It looks a little bit funny, especially my next step down here. When we go to evaluate this one, in integration by parts, we traditionally do not put a constant down on here. We're only going to put a constant down once we get to our total final answer. That way, we're only dealing with one constant overall. So on the left, we're just going to put in f of x times g of x. We do have symbols for those. F of x and g of x are going to come in as a u and a v. On the right, let's take a little bit of extra time just to format this. This is the antiderivative. I want to change the order to g of x times f prime of x dx. The reason for that is f prime of x dx is just du now. And this part is going to be v. We can do that again and go plus. This one's already in a decent format, but just for parallelism, let's write it down again. F of x times g prime of x dx. Like before, this f of x here, we're going to indicate as u, that function. G prime of x dx, this is a differential, dv. So at this stage, we can put everything together. On the left, we have just uv equals, on the right, g of x, follow the color coding, g of x is a v, and f prime of x dx is du. Then plus, one more time. So f of x over here is u times g prime of x dx is just a dv. So here we have it, folks. This is our formula for integration by parts. And here's another weird fact about integration by parts is there's really three competing formulas. It just depends on what's you try to isolate on one side of the equation. This works out. This one works out as well if you isolate u dv, and other people might isolate v du. Really, it's not too irrelevant on which way you go, but you do have to pick a formula, so our author went with this route. Isolate u dv, that's this portion right here. It's a strange equation, but this is an algebraic expression. You can do the same thing you normally would. We're going to subtract the integral of v du from both sides and write this portion right here. Let me fix my color coding first. The integral of u dv is going to be equal to uv minus the integral of v du. So differentials are weird, and when you look at this statement down here, we get a really good intuitive feel on just how weird they can get. We introduced two differentials, and through that, you can now undo the product rule. This is what it looks like. It's really, really messy, but we'll practice with it quite a lot. It'll become second nature after a lot of good practice. Well, any questions, folks, with the derivation? Okay, well, again, the big takeaways are we practiced the product rule, we got to show how to derive the formula, but also more importantly, we're seeing how this table comes into play. This is essentially step one in integration by parts, come up with that table, which means you have to pick a value for u, and you have to pick a value for dv to solve the differential equation to get the value for v. We'll put that all together and practice a whole bunch of examples down below. And I have a reminder, last semester class ended at 8:07. This is so confusing. We end at 8:37. I'll just put this in front of me. Well, let's go and try some problems for real down below. We'll come back to this remark, but like the remark is saying, this has a product inside, so if we're integrating it in a roundabout way, we're unwinding a type of product rule. However, to do that, our step one looks like this. You have to indicate what u is. Some folks might already know a really great choice for u. You also have to indicate what dv is equal to. So this portion, once again, is step one. Well, if you can pick u, you'll know what dv has to be. So we can isolate the dv function. Really, probably better to say here is step one, sorry for folks working in Penn today, is to pick the u function. I think that's a better way to express this. And the acronym above is a very sensible and highly reliable, but not perfect, way to select a u function. You actually do have to work extremely hard for this to come up with an example where this acronym is unhelpful. So for the purpose of our course, this will always do a great job. Just be aware that you can write down an integration problem where it falls flat on its face. So the mnemonic is LIATE, however you decide to pronounce that. Well, it just stands for classes of functions. For example, L is going to be the logarithmic functions. Things like natural log x, log base 7 of x, and so on, are what is mentioned in L. I, that's going to be the inverse functions. Already that is a little bit confusing because a logarithmic function is an inverse function to an exponential. But we mean these inverse functions should be picked first, the logarithms for you. Other inverse functions that we're really thinking about down here are things along the lines of, say, tangent inverse of x. I believe our author solves this one in the reading. Maybe cotangent inverse x, and so on. So we're thinking about those functions when we say I, which is confusing because T stands for trigonometric, and these are trigonometric functions. They just happen to be inverse ones. Anyone have a guess on what A should be? Absolutely, good call. So A for algebraic. And by algebraic, what we're meaning here is stuff along the lines of x, for example, or maybe it's x cubed minus 7x squared. So that kind of stuff qualifies for the A portion of the mnemonic. So any algebraic function, and hey, we have one right here, x ought to be a good choice for you, is what this mnemonic is saying. So the last one is T, trigonometric. There's an R in there somewhere. So for trigonometric, we of course mean the 6 trigonometric functions, sine, cosine, tangent, and so on. And finally, E, we mean exponential. Let's put some examples. By exponential, we might mean e to the power of x, or 7 pi power x, and so on, those kinds of functions. So this whole mnemonic tells us a way to pick the function u. Through the chat, Carrie says, is that superscripted symbol a y? Oh, up here, this one should have been an x. Is that what you're referring to? Oh, the subscript. So let me see here. Well, probably over here, the logarithm. So this one right here, gotcha. So this one should have been just the number 7. And let's see. That's the only one I see for a subscript there. So this should have been a 7, not the letter Y. Does that help out with that question there, Carter? Oh, gotcha. Yeah, sorry about my commas. I draw a little bit weird sometimes. I'm not sure why I got in the habit of doing that, but I'll try to be a little bit more clear with those. Yeah, so these were meant to be just commas. Thanks for pointing that out. Other questions at the moment? And thanks for your question, by the way. Sometimes my penmanship does go sideways, like if my hand is getting too tired or I'm just getting too tired. So if anything just looks funny on the paper, never hesitate for a clarification. I appreciate that. Well, here's our process to help us get started on integration by parts. Step 1 is to analyze this function. We have here an algebraic function x. Hyperbolic sine is playing the role of a trigonometric function. It just happens to be a hyperbolic version of it. So we can now say u equals x. And then in step 2, we just fill in everything else that's left inside this integrand. So we mean by that hyperbolic sine h of x and dx. So at this point, this part went here. And from this part, we have all the rest of the integrand, including the dx. Yeah, go ahead. Sorry, say again. H for hyperbolic. These are pretty bizarre functions. And you know what's weird about hyperbolics is sometimes Calculus 1 instructors do not cover them. So let's put just a quick expression on both of these. You know, what's pretty bizarre about the hyperbolic functions is that they originate from the equation x squared minus y squared equals 1. So this is where you're getting your hyperbolics. Your ordinary trig comes from the equation x squared plus y squared equals 1. So we use the unit circle here in order to get all of our trig functions defined. But once we go to hyperbolic functions, we're using x squared minus y squared equals 1. Now let's define this one right here. It turns out hyperbolic functions are the easy ones to define. Trig functions are a lot harder, and that's really kind of weird. They just may be more applicable, depending on who you ask. So sine h of x, really fast to define. It's e to the power of x minus e to the power of negative x divided by 2. Hyperbolic cosine, cosh x, is going to be e to the power of x. Then we'll go plus e to the power of negative x, all divided by 2. In other words, these functions are highly similar. They're built out of exponentials, linear combinations of them. And the only difference is sign in the middle is negative. And it occurs to me, if we put down some hyperbolics, we should say they're derivatives as well. I'll leave this as a check for you folks if you're curious. If you differentiate hyperbolic sine and carefully run through the chain rule, simplifying as you go, you get hyperbolic cosine. Much like the derivative of sine is cosine, that's about what we would expect. So we can say here, sine h of x prime is hyperbolic cosine of x. I say this in a couple ways. Sometimes when I have enough energy, I say hyperbolic cosine. If I'm running out of energy or just breath, I just say cosh x. There's a standard way to say it as well. So the derivative of hyperbolic sine is hyperbolic cosine. Here's where the pattern breaks down. We know the derivative of cosine is negative sine, but the derivative of hyperbolic cosine is hyperbolic sine. So a little bit of a pattern change here. You can differentiate these multiple times. A negative sign does not come up in front of the functions. They just oscillate between one version and the other on higher and higher order derivatives. So now that we've got that down, that's pretty important because our next step is to fill out the last two parts of these tables. Thanks for asking about the hyperbolics, though. Part of the first week is just to kind of review, and that's a very good, excellent portion for reviewing. Other questions at the moment so far? Okay, let's go to step 3 next. In step 3, we take a differential. Just like we've been doing all along in these notes, we're doing the differential in this column. So it turns into du equals the derivative of x is 1. So we can write 1 times dx. Or if you didn't write 1 at all and just said du equals dx, perfectly fine way to express that. Sometimes I do put in the 1 just to say, hey, we did differentiate it. We didn't forget. There's the result. So there's step 3. Step 4 is a little bit different. Let's put down a formula here just to convey how step 4 really goes. If you look at this expression here, it is literally a differential equation, but it's a nice one to solve. It turns out v is the antiderivative of dv. So in other words, all we need is an antiderivative of hyperbolic sine. Here's where the blue stuff comes into play. Think of this as the integrand on the right. Hyperbolic sine, if we take the antiderivative of that, we would get hyperbolic cosine. So this turns into cosh x. But probably a little bit more to say right here is we don't just put in any antiderivative. We want the simplest one possible. So we do not include plus c here. In this context, we're going for the simplest antiderivative to come up with a v function. So it's a 4-step process to build out the table. That makes sense. It's a 2x2 table. The last step is to put it all together. There we go. Any questions first, folks, on just coming up with the table here? Yeah, go ahead. Oh, that's a good question. It's kind of just by elimination. Once we picked x is u through the acronym here, mnemonic, what we do for this part here, hyperbolic sine x dx, is we just take everything else that's remaining in the integral. So this process says pick a u, and then everything else gets shoved into the dv expression.
So if we think like something in the middle of it, like if we use sine of 3x and we use that 3x again, would you just use the 3x of the u and then just be sine of u?
Sorry, I lost a little track on that. Let me write it down. Just it was, you said 3x, sine 3x?
Just sine 3x.
Oh, gotcha. For this one right here, it turns out this would be a whole new method. This one would just be by u substitution. The only reason integration by parts comes up here is because we're taking a product, x times the hyperbolic sign. So that's when the integration by parts comes up. That's a good thing to put here on the notes as well. The product, or you could just say the multiplication you see here indicates integration by parts is the pretty useful method on this one. Whereas down here, this one turns into a u substitution, but this is super confusing because that one is integration by parts, and I only have one thing in here. There's nothing multiplying it. So there's a lot to think about with integration by parts, but this is a good starting point. If you notice two functions multiplying, then you need that technique. Other questions at the moment? Okay, well, we are now at step 5. Here's where we finalize. We're not going to take this much description every time we solve it, but when we're starting out a new technique, I try to give a step-by-step guide just for the first one. So if folks like that type of a process, we at least have a structure. So here is finally step 5. Pretty much the conclusion of the whole process. We're going to take and integrate x sine hx, hyperbolic sine of x dx. And really the first thing we should do is write down the formula. If you forgot, no worries, but if you write this down, every single time you do integration by parts, this is a great way to just really have this learned down pat for the purpose of exams. I do give a formula sheet on the exams. They're going to be pretty detailed, but the formula sheets aren't too helpful unless we're very highly familiar with the formula itself. So the formula goes uv minus the integral of v du. So that's our setup. But now we just go back up to the table. This is its purpose, and just plug in the values that we need. So on the next line, u is x. There it goes. That wasn't so bad. V is cosh x, so drop that in for v. Minus the integral of, over here it's saying put in v again. So hyperbolic cosine goes inside. For the part where it says du, you go back up here and put in 1 times dx, or just dx by simplifying. So if we redo the color coding, here's another way to kind of just visualize this. If this is our u and v, it goes into these locations. And for the du, it came inside here. So that's our setup on the integration by parts. Notice this one element of the table we don't use when we come down to this expression, but we still need it because it informs us on what v actually is, so we can drop it in down here. Other thing to notice in integration by parts, I mean, you probably noticed it just by the formula right here, is you're not done even after you get to this because you have one last integral that still has to be solved. So part of the purpose of this mnemonic, LIATE, is to pick u in such a way that that integral down here on the bottom is solvable. If we did this backwards and put cosh here, the good chances are this will be a harder integral than what we even started with. So just like u substitution, sometimes you have to try a couple things until things fall in the right place. But that's the power of the mnemonic here. If you don't want the trial and error process, this is a pretty well-targeted way to start it off. So last thing to do here then is just solve our final integral. It's x hyperbolic cosine of x minus Whether you integrate or differentiate, the hyperbolics don't change signs if it's a sine h or a cosine h. So this just turns into sine hx, add the arbitrary constant of integration. And we did it, folks. This is integration by parts in a nutshell. We would check our answer in the same kind of way. We would differentiate this, which means the product rule will come into play. And things hopefully will cancel in such a way that we get right back to the integrand. You don't have to check these for the homework, and I'll leave it up to the class on this one. Should we check this one out or move to the next problem? Any volunteers for a direction to go with that? Next one, good call. So let's go off to the next. If you did check it, just be careful of the product rule. It'll get the right cancellations to go to the original integrand. So here's our next one. W squared e to the power of negative 2w. Let's drop this onto the next page. The purpose of part B is an indication to us that sometimes when you use integration by parts, you have to use it multiple times to actually get the total answer. The indication you probably have to use integration by parts more than once is the fact that there's a power 2 here. If it was a power 5 or a power 10, integration by parts has to be used 5 times or 10 times. There's other structures and shortcuts for when that happens. But I'm not getting into the habit of asking too many high order powers here. Definitely not exams on a homework. I'm going as high as power 2. Except for this one right here. This one's different because we don't pick u as t cubed plus 2t. It's a totally different problem in its own sense. But starting on this one, here's the process. We begin with, let's see if we can color code this a little bit better. We want a u, and we also want a dv. We start with this first row, indicated in a kind of funny way. One is just an expression, the other is a differential. Here, we want to pick something either by the acronym or pick it in a way so that when you differentiate, the complexity of the expression goes down. If I picked e negative 2w, differentiating that doesn't make it more simple. It adds a constant in front of it through the chain rule. If this is your w, that does get simpler. It's quadratic now, differentiated, and it's linear. That's a huge reduction in complexity. So the acronym would already say pick w squared because it's an algebraic expression, but that's the actual reason why. We're trying to get to where the last integral you solve is not overly complicated, more complicated than the original problem. So if we picked w squared for our u function, it totally determines what dv, the differential, has to be. It's always everything else. So e negative 2w, dw goes here, and we're, in a certain sense, on our way now. So let's put in, for this column, we want a differential, so it's going to be du. Differentiate w squared, that'll turn into a 2w, and we multiply that by dw to make it a full differential expression. Much like this differential, we always have a dv and a dw, or a dx potentially. This location is the tricky part of the integration by parts table. Anyone happen to see what the value should be on this one? Exactly. So we take this, divide by that negative 2, and then you're in business. That would be our antiderivative on that one. So good call. This is one where you could solve using a u substitution, but that's where our earlier discussion came into play. A u substitution on this, in fact, let's write it out just for the sake of one more review problem. It's okay to do that, but you'll notice this problem is long enough already. This is where this shortcut shines because doing a u substitution in the middle of an already long problem does get rapidly pretty tedious. But because this is confusing enough on its own, let's just do this u substitution one more time here. It'd be antiderivative e negative 2w dw. In this u substitution, anyone have a good pick for what u should be? Good call, folks. Negative 2w would go in. And now we need the differential of this. So du would be equal to negative 2 dw. Here's where a big difference comes into play. Let's make a comment right here. Oftentimes when we do a u substitution, we sometimes divide out these constants. It does make sense. There's no -2 here as a coefficient. So dw could be better understood as -1/2 du equals tw. But down here, we do not do that division. This 2 stays right in play. Integration by parts is a bit different. We do not divide by 2 in this context. So a little bit weird, so I'm glad we're doing this u substitution here, just to compare how integration by parts does make a slight change. But then back to this problem, we have the antiderivative of e to the power u, the u is the -2w, dw over here turns into this, -1/2 du. You could put the -1/2 in front since it's just a constant. dw goes in, or excuse me, du goes in. I even highlighted that to help me out, but at this stage, we're just about done. We get -1/2 e power of u plus a constant equals -1/2 e to the power of, that was meant to be a u. Let me fix that there. And we throw in this -2w plus a constant. So that's the long forward process. That's the shortcut down below. And Jonas says, is it safe to use the same LIATA acronym for u substitution? You know, it turns out u substitution is kind of its own thing. The acronym is probably going to be less successful there as compared to integration by parts. I would say for u substitution, the best thing to think about is pick for u a function that's inside another function like this one. So that's your best pick for u. And unfortunately, the LIATE acronym does fall short in u substitution. Other questions at the moment? Okay, well, at this stage, we're about ready to get going. If you take this extra step, you'd write this is equal to uv minus the integral of v du. Purpose of this is just to help us plug in the right elements. So we have uv coming into as this part and this part. So we kind of go diagonally through the table on the first portion, w squared multiplied by -1/2 e power -2w. Then minus the integral of v comes into play again. V is this whole thing. So -1/2 e -2w. It's also multiplied by du. That's this portion. So 2w dw goes inside. And we read through the first iteration of integration by parts. Our hope is that this integral here is simpler than the one that was over here. And is it? Well, it looks just about as hard, but one good thing did happen. It's w, not w squared. That's progress for us, even though it's a lot of steps to get there. Well, we're going to finish off this, maybe simplify and then integrate. Then we have to do another integration by parts table, and we'll move through the problem. So we've got putting these together, making it read out a little bit better. -1/2 w squared, e power -2w. Over here, we have double negation. This -1/2 cancels with the negative sign here, so now we have addition. 1/2 cancels with the 2 in front, so that fraction's gone entirely, and it's just w e power -2w dw. If we can solve the last integral by the red dot, our work is finished. So one more set of integration by parts, and we'll be on our way. But you know, we're just trying to practice integration by parts, so that's a good thing in a way. Let me put a little border here to say the differentials that we saw up here, they're now out of the scope of what we're about to do in the further steps below. But if this process worked the first time, it ought to work the second time. The only difference now is that u is just going to be w to start, not w squared. dv is just going to be all of this right here, e negative 2w dw. And Carter says, if we are just substituting the pieces into the equation, where did the negative 1/2 come from? Oh, so this part right here, I think it's weird formatting on how I wrote that fraction. It really came from right here. And you could rewrite this as negative 1/2 e power negative 2w. So is that what you're referring to here with that fraction 1/2? Yep, you bet. Sorry for the weird change of formatting too. That's definitely kind of jarring. I'll try to keep these things parallel as we go to use the results. Other questions at the moment? Okay, well, the next step is to write dv is e negative 2w dw. But here's where we get to say, don't reinvent the wheel. We've solved this differential equation once. We're just going to grab the solution again. I'll grab it in this format since that's what we're plugging in. So v is just, once again, negative 1/2 e power negative 2w. On the left, the differential just goes du equals, you can say 1, that's the derivative of w times dw, or a lot of times our author would just write it this way. Du is now equal to dw, is a more simplified way to say the same thing. So from here on out, we're going to plug in the results into this location right here and go from there. So we've got, this is a lot of copying, negative 1/2 w squared e negative 2w. Well, that's not too bad. Plus, let's do the whole uv minus the integral of v du again, just so we have a structure to help us out. So plus uv minus the integral v du. Another set of copying, negative 1/2 w squared e negative 2w. And then just drop in the results. So we have u here, v here, and hang on. I think I have a problem with my du as it relates to this. That's an error. Anyone see what the mistake is on this expression? Yeah, we should have said du from the u on the left here. That was my error. So this should have been a u rather than a dw. I mean, the equation was true. It's just unhelpful. It's unhelpful because we're trying to substitute out this du with dw. And then last thing is this v turns into that expression there. So let's rewrite this again. Plus u is w on this. The v, look to the right, is still negative 1/2 e power negative 2w. We're taking away the integral of v, which is, we write this thing down a lot, negative 1/2 e power negative 2w. And here's where my penmanship starts to go sideways. Let me correct that. And then finally, that's going to be multiplied by du in yellow, which is now just a dw. We're just about there, folks. Still one last integral we have to solve. But solving this integral is, once again, the same kind of thing we did here. We have an immediate antiderivative. So the hardest thing about this problem is really, we had to organize two tables to put together the integration by parts. And then the next hardest thing about it is making sure you copy everything down exactly. It's easy to just forget to copy a negative sign, for example. So let me know if I miss anything here. Negative 1/2 w squared e power negative 2w plus, and let me backtrack on the plus, the minus, I always make that weird mistake, minus 1/2 w e to the power of negative 2w. Over here, this is going to turn into a plus due to the double negation. 1/2 is still out in front, so this is going to be plus 1/2. Now we're just taking the antiderivative of e negative 2w, which we've done twice already. This is the expression. So it'll be a negative 1/2 e power negative 2w plus a constant. Tragically here, I need one more line because this simplifies just a little bit more. So bear with me here. I'm going to take a half times negative 1/2. So negative 1/2 w squared e power negative 2w minus a half w e power negative 2w. If your hand is getting tired, it gets better over time as the semester goes. Oh, that's not a plus, that's a minus 1/4 e power negative 2w plus a constant. And finally, that's the whole process. It won't be too common where you have to use integration by parts multiple times in a single problem. I avoid those on exams because it's just so long in a timed exam situation. But watch out for them on homework problems because in a situation like this, it can and will come up. The tabular method as in like, if it was like a higher power, you're just putting more rows. Yeah, absolutely. That would work even on a power two. Absolutely. Me personally, I'm super rusty on the tabular method. I almost never use it. If you are familiar with that method or other methods, you can't lose points in this course by knowing stuff. So you're always welcome to give an alternative approach as well. Other questions at the moment? I think that tabular approach that you mentioned, it's an awesome approach. I think it was more back in the day when people would put in like power 5 there routinely.
Yeah.
Those don't come up too often really in this class. So I felt like it was not as important of a concept. And in all honesty, when you get really convoluted expressions like this and you're working in an applied setting, you're probably going to use a computer algebra system already to formulate its antiderivative. Well, let's see, we've got about, almost 10 minutes. Let's make this one the last one for the day, the mysterious one, antiderivative cosine inverse. The book does antiderivative of tangent inverse for a very similar related example. But these are such a vague type of problem that this is a good one to solve as well. The acronym or mnemonic LIATE is really in effect on this one. And when we come back on Thursday's class, for this one as well. We didn't write down this mnemonic on the other problems because if you see something like a w squared dead giveaway, that ought to be your u, unless there's something else like a logarithm that's being expressed here. But now in this acronym, you can see which letter is relative to the information inside here. Good call. That's the inverse function relative to the cosine inverse. So we're using I there. All this does for us is it picks our u. So it's telling us u should be equal to cosine inverse of x. Just for a little bit of trigonometry review, you should know that if you write cosine x like this, that's an exponent all of a sudden. You're really talking about 1 over cosine x, which is the secant x function. But if you write this, cosine inverse of x, this is not equal to secant x. This indicates an inverse function. And that's important because, just for a couple review on some derivatives, derivative of secant x is secant x times the tangent of x, but the derivative of cosine inverse of x, this is one of those derivatives where I personally review myself because I don't think they come up a lot in a Calculus 1 class, but it turns out to be this, negative 1 over the root 1 minus x squared. So watch out for where the power is expressed because it makes suddenly a massive difference on how you visualize this function. So because it's an inverse function, we have to differentiate in that kind of way. But here's how the table's going so far in integration by parts. The only thing left over for dv is just dx, so we just throw it in. That's pretty weird. And this kind of method with integration by parts comes up most often when it's an inverse trig function you're looking at. That's when this is an effective strategy where dv is nothing but dx. Kind of weird. But similar steps on the next one. Column 1, do a differential. Du is negative 1 over square root 1 minus x squared dx, coming from this review derivative up here. And I think this one is a little bit tricky. We have to think about what are we really doing to come back from the differential down to here. Anyone spot what v is?
X squared over
It wouldn't be, your folks are close. It wouldn't be neither a 1 nor x squared over 2. Very close. It'd be x. So this is one of those weird times where the shortcut of just saying dv equals dx, it's actually not too helpful, right? It would have been more helpful if we wrote down 1 times dx. And there's always a times 1 inside the integrand because of nice properties of multiplication by 1. But if you did write it in a more complicated way, we'd see the antiderivative is just x in that sort of setup. Okay, we've got 6 minutes. Let's see what we can do with this thing. So antiderivative, cosine inverse of x dx. Let's follow the system. It's going to be uv minus the integral v du. So here's our u and v color-coded, just in case that's helpful. And because I've run out of colors, I'll just use this whole thing for yellow. Our result is then cosine inverse of x. For u, v is just times x. Minus, on the next line, I'll probably put the x in front, so it's a little bit more clear what is the input to cosine inverse. This always looks a little bit weird in formatting. This is going to be the integral of v du, which means it's going to be x multiplied by, this is our du, negative 1 over the root of 1 minus x squared dx. So integration by parts is successful if and only if this integral here by the red dot is easier to solve. It doesn't look like it by just all the stuff you have to write, but it actually is. That's the tough one because cosine inverse is a complicated function to work with. But that one there by the red dot, we can attack it just by ordinary u substitution. So this one is a u sub method. The way we can probably tell just by visual inspection is the derivative of 1 minus x squared is a negative 2x. So that could eliminate the x, saying a u substitution in that sense would work. But let's simplify this a little bit more. X cosine inverse of x plus, with the double negation here, we'll have a plus sign in the middle. Integral of x divided by root 1 minus x squared dx is where we land on. So now we're ready for the u substitution process. Excuse me. U would be set equal to the inner function you see here, 1 minus x squared. So now we can formulate du will be equal to negative 2x dx. Here we already have an x dx, so this is looking really great. Negative 2 is the odd factor out, so we can divide it out if you prefer to get negative 1/2 du equals x dx. So this x dx will just turn into that portion, and 1 minus x squared will just turn into a u. So here's our next line, x cosine inverse x. Let's see here, on this integral, through the yellow, I'm going to put the negative 1/2 out in front of the integral sign. So negative 1/2 integrate. So back inside here, we have a du. I'll highlight that in yellow just to show that's what these portions turned into. The x dx turned into that. I think it might make more sense if we just highlight that whole thing in yellow. Thing on the inside is 1 over the square root of u. So that's the last integral to solve. If we can solve this one, then we'll be on our way. But you know what? Depending on how rusty you are with calculus, even though it looks like a simple problem, this one can be a little bit tricky on its own. So let's break up the process and solve it like this. If you notice you have something that might be just a little tedious, a lot of extra steps, or legitimately complicated, sometimes it's a good idea to just break down into a second column. I'm going to solve this right here on the right, and then just drop in the answer once we have it. So antiderivative 1 over root u du. What I would do to this immediately is use properties of exponents as how they relate to the roots or radical expressions. That's a square root, so it means it's just u to a power, 1/2. We need the actual exponent because if we're forming an antiderivative, we need to be informed what is the exponent to reverse the power rule. But the next thing we need for a power rule is you never want your base in the denominator. I personally find that extremely confusing. It's better if we go like this. Antiderivative of u power negative 1/2 du. So now what we've done is we've moved the base up to the numerator, negate the sign, and now the antiderivative is a lot easier to tackle. We take the base u, come right over here, and we just add 1 in the form of 2 over 2. So 2 over 2 plus a negative 1/2 will give us a power of 1/2. You have to divide by that power, which means multiply by the reciprocal, and then add a constant. And it's still not quite done because we have to say what is u. It's 1 minus x squared. So this is 2. You could keep your power 1/2. If you prefer square root, you could drop that in as well. I'll go for the square root. So square root of u, and u is 1 minus x squared, plus a constant. So we're almost there, folks. Sorry for going right down to the minute on this one. Before we finalize it, any questions at the moment? Okay, so hardest thing about this problem, in my opinion, is just starting out the table for the integration by parts up here. But then this is just your ordinary u substitution, a more complicated one. And it comes in as x cosine inverse of x. We have a negative 1/2 here. And then it multiplies the result of this antiderivative, which we worked out down here on the margin. So inside the bracket is going 2 root 1 minus x squared. And I'm going to change this a little bit. Let me know if this seems kind of funny to you. I'm going to put the constant out here instead of it in the inside like it's being conveyed in this. It seems like I did the substitution in a weird way, but that's actually legitimate in a certain sense. Let me wind it back just as one moment. I'm going to leave my final answer in this format, but to explain it, if you put your constant c here, that really is okay. You've got your constant. But then negative 1/2 distributes and you have negative 1/2 times c. C, however, can be any real number whatsoever. So is negative 1/2 times c. And so we usually convey our total answer just like this to simplify it. If negative 1/2 times c is any real number, well, so is our ordinary plus c. And an integration by parts, the tradition is just to put in one overall constant on the right once you finalize all of your antiderivatives. So last step, this is always kind of tragic when you have one small simplification, but best thing is for our work ethic is do all those simplifications. X cosine inverse x, we have minus the root 1 minus x squared plus the constant is our answer on this one. That was, oh dang, we went over a minute on that one. Sorry about that, folks. I'll try to make sure we stay under rather than over, but if we're keeping a tally, I'll make sure that we stay under on average. Any last questions at all, folks, before we call it a night? Oh, thanks for pointing that out. Sorry about the chat, folks. Where did I'm glad you found it. Sorry about missing that, Carter, but have a great evening, folks. If you do have additional questions, I'll be happy to help out. Otherwise, I'll see you all on Thursday's class. Any questions?
Hey, Professor.
Yeah.
Um, Will 7.1 homework still be due on Wednesday then? Did we finish up enough to get that taken care of?
We're gonna actually bump this one to be due on the Thursday of this week, since my habit is we have to finish all of the problems until this is considered really officially assigned.
Yeah.
So this is gonna get bumped by a day.
Okay. Sounds good. Thank you. Have a good one.
Yep, you too.
So they could do tomorrow.
Oh, no, they'll be due on, there's always a 1 week turnaround. Looks like we're gonna finish section 7.1 on the 16th, so it'll be due on the 20th.
Here, where did the X go here?
Oh, I just switched the order right here. So I took this X and just moved it out in front.
So it's the same, X, and then where did that one go? You just multiply it in there?
This one right here, yeah, I multiplied that X up into the numerator.
And then the negative cancels. And then you-
Yeah. Exactly.
Oh,
Lots of crazy little things happen in just one line. It's impressive and sometimes overwhelming.
yeah. And then, do you have office hours?
I have office hours, yeah, quite a bit of them.
them. Syllabus?
Yeah, I'm still trying to memorize them, so that's why I kind of drew a blank on that. So it looks like it's Monday through Thursday, and as well as just by sending in emails.
Okay. So I might have to cut in because my California professor in Boise.
We gotcha.
He was horrible. And so.
Oh, that's terrible. Sorry about that.
So some of these things I definitely need a refresher, so I'll probably come in there and do it.
Sounds good. Awesome.
Thanks, sir.
This was just a random question.
Sure.
Would this be an acceptable calculator?
Yeah, that's a great one
Okay.
for exams. Absolutely.
I like, because I like using this one at home. I have one of the other ones. I just like this one way more than the other
Gotcha.
ones.
Cool.
Cool. Okay.
Yeah, you bet. And yeah, Easton, I'd be happy to help you out with that. How to find DU and V. So you're referring to this DU right here and this V right here?
Yes.
Yeah, so for those two, let me take just a quick screenshot. And let me put it down right over here. So the way to get the DU on this column right here is whatever U is, it just conveys to DU. And if you have an X, it turns into a DX on the right. So the thing in the middle is, this part is the derivative of cosine inverse X. So that's the process of getting the differential out from the U expression. So just for another quick example, if U was a nicer function like 3x, we get the differential by saying from U, go du. Because there's an x, we'll have a dx. In the middle, we take the derivative of 3x, and that would just give us a 3 out. So that's our process of getting this du right here.
Okay.
And I think the v is trickier, so I'm glad you asked about this one. The process for getting the v is you integrate dv, which means you go up a line into this cell of the table. You'd be integrating 1 times dx, which would then just turn into an x. And we would just pick the simplest antiderivative, so that's why there's no plus c here.
Okay, thank you.
Yep, you bet. Thanks for asking about that.
Yep.